It's
Okay.
now recording. This is our Project 2 final design review. Yep. Our problem statement, the main goal of this project is to convey industrial rolls of paper from a manufacturing line to a forklift. One crucial aspect of this system is that the paper will be in a V-shaped cradle that will rotate 90 degrees onto the forklift. Additionally, the cradle has to transfer the loaded paper to the forklift in 45 seconds and the same amount of time going back. Since we are a three-person group, the bolted joints, for the most part, can be ignored. Uh, our design overview of the gears. Gear 2 is connected to the crank arm and gear 3. And it has a pitch diameter of 608 millimeters, 45 teeth, a module of 8, 26 RPM, face width of 80 millimeters. Gear 3 is connected to gear 2 and the bearings and the cradle. It has a pitch diameter of 304 millimeters, a 20 teeth, a module of 8, 1/3 RPM, and 80 millimeters of face width. On the right, you can see our diagrams. Uh, this includes two free body diagrams of the gears and a static force analysis.
Going on to the design overview of bearings. We decided that it would be a rotating bearing and really just one force applied onto it for the FBD. We have force applied going to each point of the bearing. So figuring out the life rating we needed for the bearing, expected lifetime is 10 years or 3,650 days. Weekly hours of stress is 80. Daily hours of stress is 16. And number of rolls transferred and 1 hour 30 rolls. But the main idea is that it has to go for 8 hours for one shift, 8 hours for another. So 16 hours for 5 days a week for every week for 10 years. Other important factors, we have two bearings in the back of, well, in the middle part of the section where it's moving up and down the paper, and it's in a series, so both of them have to work for the system to work. For the bearing, one load is applied, and it is the weight on the paper, and each bearing has a reliability of 90%.
This is a design overview of the crank arm. How we solve for the crank arm length is we took the translational movement across the power screw in order to induce one rotation of the cradle, and we called that alpha. And then we had the initial the initial angle that the crank arm has. We called that alpha. Or I'm sorry, the translational movement is omega and the angle is alpha. Um, from there, we took omega and divided it by sine alpha, and that turned into our length, which was found to be 1.2 meters. A quick design overview of the power screw and motor. We found that we got a major diameter of 12.7 millimeters, a coefficient of friction assumed to be 0.2, a pitch of 0.453 millimeters, and a lead of uh, zero point 0.9 millimeters. A torque when lowering of uh, 125.2 Newton meters and a torque when raising of 158.7 Newton meters. The no slipping value was 7.57, which is over zero, which means that during lowering, the power screw will not slip. And over on the right, you can see a diagram of what goes on with the power screw during the lowering and raising process. This is a technical analysis. of our design. Uh, Gear 2, 3, and 4 assumed to have a max force of 111.7 kilonewtons, a stress of 100. Gear 2 has a stress of 101.5 gigapascals, but the strength of steel is 350 gigapascals, and that leads us to a 3.45 factor of safety. Um, for gear 3, the stress is 106 gigapascals, and then we have a 2.76 factor of safety. The power screw has a stress of 160.6 and a factor of safety of 2.78.
And when you get to the bearings, it's a little bit out of order, but I went back from total hours needed, which was 41,600, which was calculated by from previous slide talking about the total lifetime needed. Um, the force applied was finding the weight of the paper at times, the force of gravity, and then with all that information, I had to find the revolutions per minute for the sorry, I have a little bit of cough. Found the revolutions per minute for the bearings, which got the total lifetime revolutions. And then putting in the equation for just regular, getting the revolutions and working back, I wanted to find the dynamic load rating that the bare minimum it needed to be for a bearing, which was 7.59. And then obviously we wanted a factor of safety, so I multiplied that number by 2 to get 15.2 kilonewtons.
Here's our code. Stop to pause the video to check it out if you want to. Key outcomes, cost minimizing features using Python, multiple different combination of gear modules were tried to produce a satisfactory factor of safety. We included the weight and torque applied by steel to ensure safety of the design. We knew what time we needed to get to, so we worked back from that there to look for the cheapest modules that still hit our expected outcomes. And our points of failure. In our design, the motor rotates as the power screw rotates. It would be better if a slot were to be created in the crank arm to allow for movement down the power screw without the motor rotating. Another point of failure would be the analysis of the bolted joint. Since we are a group of 3, it was outside of the scope for this project. And finally, these components should be preloaded for optimal performance, as well as greased.
Here's
And
the
our
bill of materials. For simplicity, we chose the same steel type for all components. Uh, the bearings and the power screw can be purchased from manufacturers like McMaster Car. Gears of this size would need to be custom ordered. There are many such companies, such as like Gear Rack, and we would get numbers approximate to these.